And I'll start the webinar. As I said, I'll just let a few people come in. People are coming in now.
Beautiful. Do you normally have a list of attendees down the side, or do you keep them hidden?
We can see it. I'm not too sure if other people can see it. I haven't been on the other side of it. All right, I might get this started, Joel. Welcome everyone to Builders Declares Australia's 21st webinar on the importance of ventilation in your home. My name is Hamish White. I'm one of the founding members of Builders Declare and directors of Sanctum Homes, and I'll be your host for this evening. I'd like to begin by acknowledging the traditional owners of the land on which we meet today. I'd like to also pay my respects to elders past, present, and emerging. There feels to be a groundswell in the building industry at the moment, particularly from a client's perspective, and maybe not necessarily from a code perspective, but that is changing, for people wanting to live in a more energy efficient, comfortable, and healthy home. I know in my business, clients are wanting to know in particular how airtight we're going to make their home. And in that scenario, are we going to need ventilation or mechanical ventilation? However, no matter how tight we make our homes, ventilation is critical in the overall performance and health of our buildings. Today, we are joined by the HRV guru and overall ventilation legend, Joel Seagren. Joel is a mechanical engineer and National MVHR Solutions Engineer at Fantech. He has a passion for helping deliver energy efficient, healthy, ventilated buildings. Joel is also a former director of the Australian Passive House Association. Today's webinar is brought to you by one of our personal favourites and great mates, Passive Tech. Drew and his team are the go-to installers for Fantech products, including their flagship HRV units from Zender. Passive Tech also offer supply and installation of AC and wall-mounted bulkhead systems, heat pump hot water supply and installation, and blower door testing. And if you have a spare hour or two, a good chinwag on the phone to nerd out about Passive House. I swear to God, that guy would talk underwater. You can get in touch with Drew from Passive Tech on 0404 336 421 or drew@passivetech.com.au. You can also get in touch with Drew via Joel and his team at Fantech. All right, let's kick off today's event. The information you're about to receive is based on the experience of the presenters and may not relate to your own situation. If you'd like more specific advice, please get in touch with us via email. Like usual, today's webinar will be around about 45 to 50 minutes. We'll then have around 10 to 15 minutes to answer any of your questions. I do encourage all of you to pop in any questions in the chat or the question box below, and I'll jot them down, or I will jump in and ask Joel as we go. So Joel, over to you.
Beautiful. Thanks, Hamish, and thanks for the lovely introduction. And thank you to the Builders Declare community and all of you out there for putting aside some time to chat today. So hopefully I can instill some knowledge in you. And as Hamish mentioned, we get to the end. That's the time to pick out all the bits I've missed. I have got a reasonable number of slides and a reasonable amount of content to get through, so I will slip through fairly quickly, but hopefully it'll make sense and we can patch up any missing bits. So the importance of ventilation in your home. So it is going to be a resi kind of focused talk. So it's not going to be about commercial ventilation buildings. Not that they're horrendously dissimilar, probably just slightly less relevant to the current audience. So what is ventilation? Obviously the first part to start. So it's really just the process of bringing outside air into buildings to displace contaminated air. And we kind of define it that way just to discern it from a ceiling fan, for example, which just mixes internal air. So ventilation is really about displacing indoor air with some outdoor air. How does ventilation occur? So there's probably two real ways. One is naturally driven, so driven by wind or heat, so climate or environmental factors. And over on the right there, there's a couple of images. showing kind of cross ventilation and stack ventilation, which requires different temperatures that you're probably familiar with. And the other one obviously is mechanical ventilation, and that's where we use some energy and fans to drive airflow. Fairly simple. Don't windows adequately ventilate buildings? So that's probably the crux of what we need to cover as part of this conversation. Now, historically in the residential space, that's kind of what we've all assumed for a long time and going well back into history. But in fact, there's plenty of studies, and this one here done by a gentleman by the name of Wolfgang Feist. You might know him from Passive House Circles, basically studying contaminant levels such as moisture and CO2 inside residential type buildings over an extended period to understand the use of windows and how they, whether they sufficiently dilute contaminants. And we'll talk a little bit more about what these contaminants are later. But in essence, essentially for adequate air change to go on, we need to open the windows at least 4 times a day, and for sort of 6-hour intervals. So there's quite a regimented regime needed for windows to be a good solution. And there's some other compromising factors or necessary factors that also mean that windows might not be the best ventilation solution for your project. I'm being a little bit facetious here, but I've said windows work awesomely well on these days. If you've got outdoor temps between 18 and 25 degrees, and they're kind of defined as your comfort temps, if there's a gentle breeze blowing in the design direction, so the way you've set up your windows for cross ventilation, there's low outdoor noise levels, good outdoor air quality, meaning it's got no dust or pollen or other particles in it. Security is not a concern. And the occupants remember to open the windows and close them as needed. So as I said, a little bit facetious, but you get to see the picture that for many buildings and many occupants, there might only be a small proportion of the year when these things all fall into place. And so this is where mechanical systems can come into play. Probably the next question, and a horrible one I hate to hear, is doesn't air leakage into our buildings provide ventilation? And at first thought, maybe you stop to consider that that's a possibility, but in reality, it's never an acceptable method of ventilation. And in fact, we really refer to as infiltration, not ventilation, because the immediate questions that follow are, so where's this air coming from if it leaks into our building? Is it coming via a roof cavity, the garage, an adjoining apartment in a multi-res build? How much is coming in? Is it enough to displace the contaminants? So it's really an uncontrolled process of unknown quality. And so it's really not a suitable solution at all to say, hey, my building's a bit leaky, therefore it's well ventilated. So what contaminants are we looking to remove? We're looking to take out carbon dioxide, and that's something that results from occupants. So it's exhaled by occupants as part of the respiration process. It's also a result of cooking with gas. So good complete combustion at a gas cooker will give you carbon dioxide as a byproduct. We've got moisture. So that one's pretty obvious. Again, where the respiration process is releasing moisture. Particularly overnight in bedrooms. That's a fairly big one that we're probably all intuitively familiar with. But also drying of clothes, again, cooking, volatile organic compounds or VOCs. So these are gases that are released from carpets and other kind of synthetic materials. So it might be Laminex, it might be new fabrics, couches, things like that. And these compounds are moderately harmful to health in sufficient concentration. And the other obvious one is dust and pollen, or what we could probably group under the particulate matter, and in fact PM 2.5, where the 2.5 there refers to 2.5 microns, so it's talking about a size of particle which has been studied and found to be one of the more harmful sizes. So it intrinsically makes sense that the big stuff that's floating around that we can see, not so harmful, pretty annoying, gets on us, maybe gets in our eyes, but it's not the size that can make its way in through our respiratory systems. And that's kind of where that 2.5 size is particularly concerning. So as you can see, there's a number of things we're looking to remove that accumulate inside our building. Most of them start off inside our building. So including dust and pollen can be walked in on people's shoes or clothing and things like that. So we're not really considering these things have come from outside to get in. They're actually internally generated contaminants. So what's an MVHR system? So we've talked about ventilation and kind of why it's necessary, and we'll continue that journey around why ventilation is necessary. But specifically what we wanted to talk about is MVHR systems, or mechanical ventilation with heat recovery in the process. And there's some good reasons why we might want to introduce that style of system. Now, just to give you a really quick overview of what conceptually what mechanical ventilation with heat recovery is, I've added a couple of diagrams there. Now, if we look at the winter side one on the left there, it's essentially a process whereby we bring outside air in, which might be at quite a low temperature. Here we've sort of said -5 degrees. And we bring it in through that sort of odd-shaped hexagonal heat exchanger at the bottom. And as we do that, we remove extract air, or we can call it maybe exhaust air as well. So traditionally that's done by our bathroom exhaust fan and just ditched to outside the building. But in this case, we're actually going to bring that air back through the heat exchanger also and recover that thermal energy. Ideally, the inside of our building being a bit warmer. Either we've had some nice solar gain or we've used a little bit of heating. And rather than just dumping that exhaust air outside, we're going to recover the thermal energy. Now, the same process works in summer, except now we've got higher temps outside and lower temps inside. But in essence, heat transfer is heat transfer. And we can do this in a nice, efficient manner at efficiencies up to sort of 90, even 95%. So we can do that really cleverly and with really low power consumption that might only be, for an average 3-bedroom home, might only be sort of 35 watts. So quite a low power consumption process. There's essentially two types of these ventilation systems. So there's a centralized one, and a little bit like it sounds, you can see that there's a unit and there's a network of duct throughout the building. And if we look at what a typical drawing looks like there, a layout plan, and this is something typically a supplier of this equipment might give to you, it'll sort of spell out where you need to run the duct to and which zones of the building are going to be supply air zones and which ones are going to be extraction zones. And in essence, the rule is really anywhere that's wet or odorous. So essentially we're going to remove odor and moisture from certain parts of the building. And so intuitively that makes sense that there's the kitchen, there's a laundry, there's a powder room, walk-in robes could fall into that category, mud rooms. And conversely, we're going to supply the same amount of air that we're extracting into what we'll call habitable spaces. So places we sit and spend time in. So lounge, bedroom, dining, studies, rumpus rooms. And that way, by having a balanced amount of airflow on both supply and extract, we're operating in the most efficient manner. And we're not trying to force airflow through our building fabric. We're not reliant on leakage in or out of our building in order to facilitate that ventilation. You'll see at the bottom of the page, we've obviously got a supply air or an outside air intake grill and an exhaust air. So just those two external connections. That's typically what a MVHR ducted system unit would look like. So we've essentially got a unit casing, and to give you some idea, for a 3-4 bedroom type resi project, these are typically going to be around about front loader washing machine size, with ductwork kind of rising off the top. So on the right hand side, that's kind of your case. You can see a fan in there. There's a second fan in there, as we could see from the previous slide. 2 fans, one on the supply side, one on the exhaust side of the system. In the middle, we've got the heat exchanger. And over on the left-hand side, we've just got a bit of an illustration that kind of shows that heat recovery process. Warm air on one side, cool air on the other, and we're transferring heat between those 2 airstreams. Now, the heat exchangers are made really carefully so that there's absolutely no mixing of that air. The last thing we want to do is contaminate supply air with extract air, which might have toilet odor or kitchen odor or moisture or any of those things that we don't want. So really cleverly built and of really high efficiency setups. The other type is what's known as decentralized. And for smaller type projects, these might be applicable, or for retrofit projects where it's not possible to get duct systems in place. And so these actually go through horizontally through the wall of the building. Now, they will be lower volume, and they typically will only do a single space at a time. And if we have a quick look at what's in those, in this particular style, there's a wall tube. And if we look over on the right, it's actually kind of split in the center. So it's actually got 2 airstreams. So it's equivalent essentially to having 2 penetrations. And conceptually, that's essentially our outside air intake and our exhaust air that we saw on the previous couple of slides. So we've got a wall tube, we've got an internal heat exchanger, and we've got a couple of filters in that process as well. I would say, I did miss saying that the ducted system also has those filters in there. And typically they are sort of G4 F7 grade, where F7 is filtering your supply air to a sufficient point to take out all those sort of pollens and PM 2.5 particles. Why do we want to use MVHR systems in particular in buildings? So indoor air quality is the obvious one. We've kind of covered that in the ventilation introduction. We're looking to displace all those contaminants, remove those, and provide some fresh filtered air. But why else are we looking for MVHR systems particularly? And the next obvious one is a reduction in heating and cooling costs. So it's conceptually fairly easy to understand that in summer and winter, if we open our windows, as we were kind of advised to, for 4 times a day for extended periods, we're going to be thermally letting cool or warm air into that building. And if we're going to maintain comfort conditions, we're going to need to run some heating or cooling. And obviously up goes our utility bills in that process. The other part to it is increased comfort levels. So whilst we can turn on our heating or cooling and we can drive temperatures into the range that we find comfortable, it doesn't fully alleviate the discomfort that happens in that particular room whilst that process happens. So obviously a breezy day, middle of winter, you've got a window open for ventilation reasons. You've got that cool airstream coming in there, and before it gets to your heating system, there's actually some discomfort for anyone who's remotely in the vicinity of that open window. So comfort is actually a significant part of that, not just the energy efficiency process. In order to expand on that a little, there's a really good case study that was carried out by Zender, and it's probably more accurately described as a research project that ran for 12 months. And it was carried out by a gentleman by the name of Bart Kremers on an apartment block for apartments in Buren, which is in in Holland, near Amsterdam. And it basically set up an experiment where the bottom two apartments had ventilation systems. We can see their bottom left and right had ventilation systems, and the top two apartments had windows only. You can see the number of occupants, cats and dogs and people that were in each of those spaces. And for all intensive purposes, the apartments were of similar size, similar number of windows, and no specific instructions were given to occupants about opening windows. You must open at this time, that time. They were left to manage the building as they historically would have before they'd moved into this new building. And so it was a fairly nice controlled study to understand the benefits of ventilation systems. Now we can see down the bottom there the two different ventilation rates, one on the left being a little bit lower than the one on the right. That's partly about size. You'll notice the right-hand side apartments are a little bit larger. Plus, also we'll add in the fact we've got a dog there, so it maybe counts as half an occupant. So the summary of that after a year's worth of analysis was essentially to try and produce a good visual understanding of air quality in those apartments. Now, typically in the ventilation space, a really good proxy or indicator for ventilation level is CO2 or carbon dioxide. Now, it's typically measured because it's moderately easy to measure, and it's also a good indication, as I mentioned, of whether sufficient ventilation is occurring and whether other contaminants are likely to be about if it's not occurring. And so whilst 1,000 parts per million, which is kind of where we've gone from the orange to the bad air quality, it's not imminently a health threat. It's kind of a level at which we start to become concerned about inadequate ventilation. And so in this plot here, what we've shown going from kind of left to right in each of those, we'll call them horizontal bars, are the number of hours across the year. So on the left-hand side, we're starting at kind of hour naught, and at the right-hand side, we've got to the end of 8,600 hours or something like that exist in a year. And what we've tried to show here is for each of the spaces, so the living room, the bedrooms, you'll note the right-hand apartments are the only ones with second bedrooms. We've shown the number of hours where the air quality was deemed to be poor. So anywhere that it's red is actually in that poor zone. And so you can see the upper two units that have no ventilation actually have quite high levels of poor air quality by comparison to the bottom two. And if we drop onto the next one, we can actually quantify the number of hours where that air quality has been above our 1,000 parts per million, which we're setting as our threshold for acceptable air quality. Now, as we mentioned, if there's high levels of CO2, there's probably high levels of moisture, there's probably high levels of VOC, and there's potentially good levels of particulate matter as well, particularly animals and so forth in the building. Often particulate levels can be a little bit higher. The airing factor that they used there was basically talking about what proportion of time those windows were open. So moderately similar. They weren't given, as I said, specific instructions, but they were actually, the windows were used in a relatively similar manner between upper and lower levels. And conceivably, they were probably when climate conditions were good, when it was a warm day, the breeze was not too strong, they weren't worried about security. But what we can see is there is, in fact, virtually 50 times the number of, we'll call, unhealthy hours in those upper level apartments compared to the lower one. And the study went a little bit further to even say, hey, what's the heating and cooling difference in those approaches? Obviously, whilst they had their windows open for that amount of time, there was cold or hot air getting into those buildings. And we'll keep in mind that it is in Holland, which has got fairly cool wintertime periods, and actually found that the heating use in the bottom two apartments was 24% less and the cooling use 35% less. So not only is there an air quality thing or an air quality performance improvement, there's also a significant heating and cooling use that's associated with that window use. I guess the next part to cover is what attributes are required to integrate MVHR systems. And so in essence, it's really just about building fabric air tightness. And that leads always to the next question, how airtight is enough? We probably need to quickly look at the concept of air tightness, just in case someone's not familiar with that already. And in essence, we measure air tightness of buildings using blower door testing, which, like it appears in the image, is just a series of fans where we seal up a doorway and we put a fan, one or more, into a building. This one's actually a commercial building. So just to show that the concept extends all the way from a tiny one-bedroom studio up to a multi-level office building. And we supply enough air, the fans run, deliver enough air into that building until we can maintain a certain pressure. And that pressure is about 50 pascals. And then we report that figure, how much airflow was needed to maintain 50 pascals to give us an idea and a comparative indicator of how airtight that building is. It's probably critically important also to talk about why air tightness is important. Because one of the things we probably don't want to work or allow to permeate is that if I build in an airtight manner, I need to ventilate. So why don't I decide I won't build in a very airtight manner? That way I avoid any additional cost. So that is a fairly flawed bit of thinking because air tightness carries with it a lot of benefits. One of those is that air leakage into the wall and roof assembly carries moisture with it. So we might think of it just as air, but air always has some degree of moisture in it. And that air, when it finds its way, warmer air finds its way into a cooler surface at a given time of year, creates condensation, creates a mold risk. Air leakage creates unwanted heat gain and loss. We've seen, obviously, in the last 20 years, all the attention that's gone into insulating buildings, providing better wall, ceiling insulation. And that's definitely improved the thermal performance of our buildings. But if we're going to take that next step and make them even more efficient again, adding extra insulation is going to do very little for us. Going from R6 to R8 is a very diminished benefit. And so one of the last remaining untapped areas of energy efficiency improvement is actually air leakage. It's actually getting your building leakage rates down to reduce your energy consumption and heating and cooling. And the other obvious one is that air leakage can lead to lower indoor air quality. So like we talked about before, if we relied on air leakage for ventilation, we don't know how much air and we don't know where it's coming from. We also know from bushfire events and bits and pieces that we can get plenty of external contaminants into our building. The next question that obviously comes along is that, okay, at what point is ventilation going to be a necessary requirement? And to me, it makes no sense to try and describe a particular threshold or a particular rate at which HRV or MVHR or exhaust fans become necessary or not necessary. It's just not a two-sided. It's not a this or a that kind of approach. It's a linear scale. So I've facetiously again called it the Seagren scale of airtightness versus ventilation product benefit. So at one end on the left-hand side, we've got 10 meters cubed per hour, meter squared. And so I've actually got out of my old ways of using air changes per hour and started using what's better industry practice these days as permeability. Now, the good part for residential builds, so houses and so forth, is that they typically land roughly about the same. So for those of you who might be familiar with air changes per hour, that's roughly the same as the permeability value for a residential building. For a really complex geometry type building, it's not going to be the same. On the right-hand side, a permeability of 3. So I've given you that kind of spectrum. Those of you who are familiar with passive house probably know that it sits down at about 0.6. So even further off to the right-hand side. But what I've tried to show here, and without any delineation within that range, is just the spectrum of products you might consider using to achieve ventilation. Obviously, right out at the left-hand end at 10, a permeability of 10, really bathroom exhausts to make sure you get rid of that moisture with on-off type operation like we're used to are probably still the right product. There's no point spending money on high-performance ducted MVHR systems when you're right out the very end in a super leaky building. But as we start to work our way across to the right-hand side, we go from on-off type operation for an exhaust fan to high-low continuous operation. So the fan will run all the time. It'll boost signals such as occupancy or humidity, but then we'll drop back down to a low baseline ventilation. We then sort of step into some entry-level sort of decentralized type stuff in combination with a decentralized MVHR in association with bathroom exhaust fans. And then as that air tightness spectrum reduces or gets tighter, we move into sort of medium performance and then high performance HRV systems or MVHR systems. So I really wanted to sort of point out there that there are a range of different ventilation solutions, but that there's not actually a magic number at which one becomes great and no good. Obviously, the high performance one still delivers benefit back a little bit further to the left, but is it as quite as cost efficient as the medium performance unit in a leakier building? Probably not. So it's about matching your spend to the air tightness of your building. An interesting note was also that NCC 2022 has got some thresholds now for continuous ventilation. And that is actually at a permeability of 5. Now, it's the soft entry into NCC is probably the best way to describe that, because air tightness testing, so blower door testing, is not actually a mandatory process. And the air tightness testing is only one of a few compliance pathways. So it's one of the ways you can demonstrate compliance with some of the building fabric requirements. I think it's probably stuff that will be done in a minority, but it's the thin end of the wedge, I think. Get people used to testing, and in time, we'll hopefully see tighter buildings that are tested more often. I've just put a couple of snippets in there from the NCC 2022 final draft, and that basically talks about the fact that it applies to class 2, so multi-res. It applies in that second piece, that H6V3, whilst it doesn't state, is for class 1 buildings, so freestanding houses. And so you can see the wording is basically the same in those. So where a permeability rate of not more than 5 at 50 pascals is achieved, we need to have a mechanical system that runs continuously or intermittently with some rules around about 25% of each 4-hour segment. So there's a recognition there that as we build more airtightly, we do need to provide ventilation there. As I say, it's not a mandatory approach. There is still other deemed to satisfy pathways to take, but that is one of the objectives, or one of the pathways that the ABCB is keen to see builders start to explore and understand. And it makes a lot of sense to build and understand what you're building. Without testing it, you really don't know whether you're building a 10 permeability of 10 building or a permeability of 2, and it helps you avoid some problems down the track in terms of mold, moisture accumulation. That can be an issue if you haven't got some continuous ventilation. On the ventilation spectrum, obviously also comes range hoods, and as part of that discussion, combustion heaters kind of naturally fall into that sphere as well. So what changes with those when we start building moderately airtight or really airtight? So if we look at range hoods, we've got a couple of types. Typically, we've got a externally ducted range hood, or we've got a recirculating range hood. Classically, in our leaky buildings, we've used externally ducted range hoods. Probably the best way to dump all our contaminated air outside. But suddenly we have this question that arises that if our building's moderately airtight and we're trying to suck 100 litres a second, which is typically what a small range hood will do, not even a mid-size or large, where's that 100 litres a second going to come from? How does it find its way back into our building? And so it's possible to do some externally ducted, but we need to think about extra systems if we're going to do that. It's a bit beyond the scope of what we're talking today to delve into what that is, but needless to say, in a moderately airtight building, a recirculating range hood is a fairly simple, practical solution. Typically with carbon filters or something like that, or plasma, as we do want to try and capture odor molecules in that process. But recirculating range hood allows our volumes to remain balanced. We're not trying to draw air in through the building or discharge air outside the building. If we look at the combustion heaters, for those who've enjoyed the comfort of a combustion heater, will be aware that there's obviously air going up into the combustion heater and out its flue. And so the question then becomes, hey, where does that makeup air into the combustion heater come from? So like the range hood, we've got a very similar challenge there. And so some suppliers have cleverly solved this issue by using combustion heaters with dedicated makeup air. So that top image on the right there shows a supply air pipe into the bottom of the combustion heater. And it's also a really comfortable approach as well, because in our conventional combustion heater, we're drawing that air from the room. And so it's going to make it a little bit drafty also. There's always going to be air movement, whereas when it's got a dedicated supply air, it works well. Bottom right-hand side, open fireplace. That's really a fairly uncontrolled device and a relatively inefficient device. And so it's really probably not something we're going to see into too many more buildings. What do I need to know as a building designer? So if we're going to look at putting a ventilation system in, and it's not just bathroom exhaust fans, if we're starting to look at a ducted system, we probably need to have a little bit of a think about what it is that we're going to need. So firstly, HRV spatial requirements. I touched on before the fact that typically a 3-4 bedroom house type unit is going to be about front loader washing machine, typically upright, but for smaller builds, there are both horizontal in ceiling and small sort of overhead cupboard sized units. Preferably they sit inside the thermal envelope, so not out in the garage or externally. A, they're not weatherproof, but B, there's some efficiency loss by exposing it to hot or cold external temps. Ceilings are typically the easiest way to distribute ductwork, and there'll be some images in a minute showing you that Or in fact, if we look at that center image there, we can see that internal ductwork there, 90 millimeter or 70 millimeter ductwork, 75 millimeter ductwork that runs throughout the building. That needs to stay within the thermal envelope because it's not insulated. In order to keep the diameter small, it needs to be uninsulated and stay within the thermal envelope. We need to provide typically about 120 mil cavity, to get the ductwork through, but also the grill housings mounted there. We need a drain point, like AC units, HRV or MVHR units will produce condensation at certain times. 240 volt GPO, some systems may also need an Ethernet point. If we look just for a minute in a little more detail at grills and grill housings, we can see ceiling and bulkhead wall types are a couple of typical ones, and you can kind of see those arrangements there. Normally it's a housing that's fixed away pre-plaster and then a grill that's applied from outside afterward. Supplementary heating and cooling is probably a good question that sort of falls in there. And people are probably keen to understand how a ventilation system might impact on that. Obviously, where we apply heating or cooling, we want to make sure it's not introducing any additional outside air or exhausting to anything outside. Our MVHR system takes care of that outside air management. So we want our heating and cooling systems to be recirculatory in nature. So split system AC, ducted AC, radiant heating, it's all fine. Panels, hydronic, high efficiency enclosed wood heaters with their own makeup air, like we talked about in the previous slide, are fine. Open fireplaces are going to be a problematic thing. And the other comment to make is that the MVHR systems run on relatively low airflow rates for indoor air quality purposes, and therefore they don't provide rapid redistribution of heat. And so we need to think carefully about the heating and cooling device location rather than assume the MVHR system is going to redistribute that quickly. What do we need to know as a homeowner? Fortunately, very little. So systems are really, MVHR systems and units are set up so that the units really are quite well self-managed. So once commissioned correctly, and they do definitely need to be commissioned, ducted systems, because out of the box, they're not going to deliver the necessary airflow rates to the required rooms. So once that's commissioned, there's really not much adjustment apart from changing some fan speeds. If you go away, you drop it down to a really low speed. If you have additional people, a party, for example, you boost it up, or you would boost it for showering and cooking and those sorts of activities. You might also change the comfort temp setting by a couple of degrees. I won't get into the nitty-gritty on that, but just an item to note. Filter changes, as we talked about, probably 6 monthly. Does depend a little bit on your outside conditions. If you're in a dust bowl, it's going to be a little more rapid than that, but on average 6 months is probably a good indicator. Crazy string is what some people have described radial duct design as, and that's a typical install there. Those of you who are sort of familiar with wraps and bits and pieces will notice there's no air tightness layer in that particular build above the wraps, but they've done the right thing and got their ventilation ductwork in under their insulation layer there. Why do we do radial duct design? It's basically about making sure we can finely tune airflow rates to each space, and also so we don't get any crosstalk. We don't get noise come from one piece of duct into a branch duct system and back down into the next area. Stepping on to a couple of advanced topics. I know we had a few quick questions, so I did scribble in just a couple of advanced topics. MVHR systems with integrated heating or cooling we get asked about. It's not something that really is particularly useful at this point in time. They're very low capacity So in the order of 2 kilowatts for a typical 200 square meter, even 300 square meter project. And that's because the airflow rates that MVHR unit appropriately sized for that project delivers are quite low. And the capacity we can deliver is proportional to the airflow rate. So we get low airflow rates needed for indoor air quality, gives us only really low capacity if we try and add on some integrated heating or cooling. And to date, these systems have been complex and not very cost competitive with AC splits. So we've actually built some in the past, installed them. They operate okay. They've only sort of ever gone into certifiable passive house projects, so right up at that kind of really high performance end of the market. And they are still marginal in terms of having sufficient capacity, and particularly in terms of responding reasonably rapidly to out of range temperatures. So let's imagine someone's gone on holidays, come back to a house that's overheated, it's 32 degrees. The ability to get that temperature down quickly is quite limited when you have very low capacity. So it's not a product that really exists in a cost-effective state at this point. Not to say that in the future there might not be some products that work a little bit better in there, but for the moment, the low capacity is probably the first problem for most projects. And then secondarily, the cost and complexity is probably not warranted versus some splits at the moment. ERV or HRV core. So the last advanced topic I'm going to touch on here, two different types of cores, often interchangeable in units. ERV standing for energy recovery, or sometimes known as enthalpy type core, and HRV being heat recovery core or sensible or temperature only type core. Now, the images below are basically representative of an ERV core. And so where we find application for these largely in Australia is in regions of high outside humidity. And without going through all the kind of small text there, the essence of that is if in tropical Queensland, you can keep the humidity levels inside your building relatively low, either through air conditioning, which is also dehumidifying, maybe a dehumidifier. As the ventilation process occurs and this cool, dry air goes out, not only do we recover the cool in that process, we also strip away the moisture. So we transfer some moisture from the high outside humidity air into the outgoing exhaust air stream. And so we can bring down the humidity level of that supply air. And that is really beneficial because it makes our indoor comfort conditions easier to achieve. And as a little side note, the amount of cooling power to cool moist air is so much greater than to cool dry air. So not only is it a temperature and humidity control thing, it's also an energy consumption thing. Why don't we use ERV more exclusively or more widespread in other regions? Well, there's actually some downside to ERV as well, and that is that it's much slower in moving wintertime indoor internally generated moisture. So let's say Melbourne region, we've showered lots of moisture. If we imagine that moisture recovery process working the same way, and rather than us expelling all the moisture from this high indoor moisture environment, we're actually going to contribute or pass some of that, transfer some of that to the outside air. And so it's going to bump up our supply air moisture. And so we actually don't want that to happen in that winter time. So particularly in cooler regions where we've got lots of that. The other downside of ERV, if it's not appropriately applied, is that the sensible or the actual temperature related heat recovery is lower. So if we're going to use an ERV type core, we need to make sure it's quite appropriately selected. And it's also a little more expensive typically than a HRV core. In order to be a little more scientific about this, we actually partnered with Zender to do some monitoring for 12 months on a Sydney project. And we set that up on a certified passive house and measured temperature and moisture inside the building. And we actually rotated a core between it rotated the core between enthalpy type or ERV type and HRV type to see what the change in indoor conditions was like. And what we found for that Sydney climate is that HRV was still significantly better. We found the small benefit in summer from ERV was outweighed by the wintertime performance and shoulder season performance. And so we're relatively confident in our recommendation that for Sydney, Perth, and everywhere south of that, that HRV is a better all-purpose core. There is special application, obviously, though, to alpine regions, and kind of for the reverse reason, in that their wintertime humidity levels get too low, and potentially applicable for a short patch to Canberra and areas like that as well. However, Canberra probably doesn't benefit enough across the rest of the year from that ERV core. So alpine regions are probably where we would say ERV core also. Hopefully that's given you a really quick introduction to ventilation, what it is, and a little bit about how MVHR systems, in particular ducted systems, might fit into that ventilation solution.
All right.
Happy for some questions.
Thanks, Joel.
Now. I
think. Very informative. We do have a few questions here, which we might jump into because we're 10 minutes to 6. So for everyone there, it's likely to run over a little bit longer. I'm happy to stay around, Joel, if you're happy to stay around to get some of these questions answered. So Sean's asked, if ventilating a pool room in a house, what would be most suitable ventilation strategy? HRV, ERV, dehumidifier? And would it be best practice to make the pool room airtight so the moisture doesn't leak through into the house?
Yeah, really good question. I actually
have no idea what project he's talking about. So,
really good question, and something that's popping up regularly. So I'll start with the last one, which is the easier one. Do I make my pool airtight? Yeah, absolutely. So high levels of moisture in the air in your pool space. You've obviously got warm water. There's no question that you're going to end up with high indoor humidity in that pool space. You don't want that drifting into the rest of your house. So definitely make your pool airtight. There are dedicated MVHR systems for pool spaces. They are not your regular house type ventilation systems. And the reason for that is that the high levels of moisture in the pool rooms actually cause, we'll say, too much condensation within a high performance narrow channel heat exchanger core. And so effectively too much moisture can block those temporarily of airflow. So it is a bit of a specialist product. MVHR systems for pools. There is a couple of good suppliers around for those products, but yeah, you want to go hunting specifically for a dedicated pool ventilation product there. They'll probably have some dehumidification function in there as well as just the heat recovery function.
And would, in your opinion, would you want to be keeping the pool airtight from the house and have them as two separate systems?
Absolutely, yeah. So firstly, you've got that moisture issue. We don't want those high humidity levels into the rest of the house. Potentially, you've got a thermal thing as well. You might want to run your pool at a different temperature to the rest of your house. And so, yeah, absolutely makes sense. You can balance up airflow rates for your ventilation system in the pool. So there's no need to have kind of that bleed under the door like a traditional MVHR system does.
Couple of questions here about the ducting. What is the size of the ducting, and where is it usually placed? We answered that question before. It's inside the thermal envelope. And do you need to clean it? And if so, how do you do that? And what kind of maintenance regime do you need?
Yeah, good question. So there's typically probably in the Oz market 90 mil and 75 mil. There's a little bit of specialist low profile duct around about 50 mil thickness. And before everyone gets excited, I would say don't use it. It's slightly lower airflow capacity and typically exotically expensive. So it's don't design your buildings around a really low profile duct where ultimately you're going to need a bit more space around your housings anyway. So stick to those larger sizes. The reason for using that specific duct, which is known as semi-rigid, and it's actually made from high-density polyethylene, has an inner and outer core, is so that it is really robust and airtight, and also so that it can be cleaned. So with 100% high-density polyethylene, it's quite antibacterial, so low chance of getting mold growth there, and also anti-static, so we're not likely to pick up dust from static issues. But it is conceivable that over time you will get some dust and so forth form. And there are cleaning tools that contractors can use. They can just pop off a grill at one end or disconnect from a manifold at the other. And there's a long whirly thing that goes on the end of a cordless drill that you plug a vacuum to, and you can essentially vac out those lines. Now, I'd suggest after perhaps 5 years, you have someone come and have a look at them. At 5 years, it's probably also worth considering whether your heat recovery unit heat exchanger needs a bit of inspection, possibly a clean up fan. So I talked about filter changes at 6 months. Probably at 5 years, it's time to also get your contractor back and say, hey, come and have a look at my core, have a look at my ducts, just check my fans and so forth. All relatively quick processes. A duct clean is not a long and arduous task, nor is a core clean and things like that. So don't be too concerned about those.
Awesome. I think we might have answered this question anyway. When should you install an ERV? And given likely changing climate, should more southern states start to consider them?
Yeah, so I'm taking that as ERV versus HRV.
Yes.
I don't think we're going to see anywhere near a sufficient enough move in climate for southern states in terms of temperature and humidity to warrant that. It's pretty clear cut. So for Melbourne, for example, we'd have to go all the way past Sydney in terms of their summertime humidity and beyond before it starts to make sense. So I think we're safely, our climate's not changing fast enough to make that an issue.
Cool. So insofar as retrofits are concerned, how do MVHR systems compare to portable air purifiers and or dehumidifiers? And then I don't know if there are single machines that do both.
Yeah, yep. So dehumidifiers are a little bit like split system air conditioners in that they are only working on internal air. So dehumidifier will pull the moisture out of the air. And if that's your sole purpose, if that's the sole objective, they are the best device to do that. So we want to get moisture out of the air. But what they're not doing that an MVHR system will do is remove contaminants from the air, in the case of a dehumidifier, or provide fresh air. Now, if we look at purifiers, they will remove some particulate matter from within indoor air, but they will have trouble removing gaseous type contaminants. So the VOCs we talked about, CO2, they don't do much for that at all. It's very much particulate-based system in a purifier. So we've kind of got two different concepts. One's about managing stuff floating around in your house already, MVHR system is about displacing all the contaminants that are in your building.
Another question from Elizabeth. Thanks for all your questions. Your suggestions on range hoods are really intriguing. I've been really concerned about whether downdraft cooktop extract fans can capture aerosolized fats and moisture from a stir fry, for example. Should she stop worrying?
Well, not as well. So if you do Google around, there are a couple of good papers around there where they've done some testing on canopy style overhead versus downdraft. And given all of the particulates and the aerosols you're talking about are hot and warm, they are rising. And so it makes a lot of common sense that the canopy type will outperform the downdraft. It probably depends on the degree of frying and cooking you're going to do. I've seen some rippingly good downdraft systems. Some of them really neat and compact, seem that their owners are really happy with. And the other thing I'd point out is that MVHR systems do have a kitchen extract point, which is there to kind of mop up most of the excess moisture and odor. We don't really want it to be serving the purpose of mopping up oil particles, fat or grease, because that's going to contaminate our ductwork fairly quickly. But excess moisture is absolutely fine.
This might be a difficult question to ask because costs around heat recovery ventilation systems are typically project-based, but are you able to give a ballpark cost for HRV for a 120 square metre home?
Yeah, so it's going to depend a little bit on that spectrum we talked about, whether you're starting at some sort of entry-level decentralized stuff, in which case you might end up at sort of $4,000 or $5,000, or at the premium end of town, you could end up at $9,000 or $10,000. So there's quite a broad range there for a fully premium, fully ducted system to a kind of entry level through wall system. So as I've kind of alluded to, the air tightness of your build and the quality of your build is going to impact a little bit where a sensible selection might sit along that spectrum.
Now, are those prices that you're quoting just supply of the units?
Yeah, so they're probably product supply. You can perhaps add, you'd add something on top of that. Again, lower cost ones are a pretty simple install, so there's not an average figure, but your install might range, who knows, from 2,000 to 6,000, anywhere in there, depending on the complexity of the install and complexity of the product.
Look, I can just talk on our experience in the units that we're putting in our homes. It's anywhere between $17,000 and $21,000 installed, but that's typically for your Q350 series. Yep. And they're the premium end for passive houses.
Yep.
How do the HRV work with bushfire smoke? And it's probably a pretty topical question, given that we're seeing more bushfires these days.
Yep. So bushfire smoke's an interesting one. It's really fine in terms of its particle size. So we talked about sort of 2.5 micron particles that HRV filters capture, our F7 ones. Bushfire smoke particles are actually way smaller than that. They're kind of down around 0.1, 0.2. And so firstly, we need to think about our building fabric air tightness. If we're not super tight, then we're getting lots of infiltration through our building fabric anyway. And so attempting to filter any more tightly than that doesn't make a lot of sense. So we probably need to be kind of right down at that passive house end of air tightness, down around a permeability of 1, before it makes sense to try and do too much filtration. There are some systems around that have HEPA grade filtration in there. They are definitely designed to be intermittent use. So because of the pressure drops and cost of filters, but specifically pressure drops and energy consumption increases that occur when you use them, we'd say only use them for a bushfire event and then take them out of the system. So essentially it's a filter housing that you would add externally, and you'd remove the filter element that's in there and seal it up again.
And this is from Jeremy. Given ERV are not generally good for cooler climates, what do we do for recent shelter season high humidity warm conditions we've just experienced in Melbourne? I assume HRV won't do much to regulate humidity under these conditions. How would you recommend controlling internal humidity levels?
Yeah, so shoulder season humidity or short-term humidity is always a bit of a challenge. It doesn't warrant ERV type cores particularly. That said, a lot of units do have interchangeable cores. So the HRV and the ERV core are the same size. And if you wanted to spend, you could buy a second core that would give you some benefit there. It may still not be enough, but sometimes that short shoulder period. And so it becomes a little bit of an economic thing. Do you spend and buy a portable dehumidifier for that short period? There's not really an extra add-on to a MVHR system that makes it makes it appropriate for short-term use. Keeping in mind most AC systems have a dry mode as well. Whether they work well or not, it's a little bit debatable, but the intent there is that they just remove moisture. They don't actually change the air temperature.
Probably a follow-on question. Can you get standalone units for dehumidification?
Yeah, definitely. They can be noisy. Again, probably appropriate for short-term use. If you were tropical Queensland and you wanted an ongoing solution, I don't think you'd probably be that tolerant of 7 different portable dehumidifiers floating around your house for longer use. So I think you probably need to look at some kind of ducted system for tropical Queensland, but the short-term use, yeah, absolutely.
This is quite a specific question to a particular building methodology, but Russell's looking to build a rammed earth house. Is HRV system applicable with these external walls?
Yeah,
Not sure if that's to do with air tightness or whether or not we want to run the ducts or not, but I'll let you speak on that question.
Yeah, so it's probably not going to have too much impact. Obviously, getting your air tightness is important. There's no reason rammed earth can't be nice and airtight, built carefully. It will give better moisture removal, and it's actually one of the reasons that HRV or MVHR systems are suggested is management of interstitial or internal wall and roof moisture levels. So the ability for that to be removed when it's soaked up by the plasterboard. If we ventilate, we can help remove that away. So where we've got interesting wall types that might hold more moisture at certain times than you like, then the ventilation system, would be really beneficial in that space.
One last question, and it's just around cost again from Melanie. And it's just, can we get a rough idea of cost for a system, including installation of an average sized home? I can speak on that just from our experience. If we're going the higher end, that's going to be 18 to 22 grand for your passive house, the high performance models.
Yep.
But you can get different units, and they might be $4,000 or $5,000 cheaper.
Absolutely. We've got probably 13 different units in our range. And so, yeah, the projects like Hamish that you're building are probably bumping 300 square meters on average, something like that. As that project size steps down, the units get a little bit more compact and a little cheaper.
So that's it. Joel, thank you so much for coming on today. I just realised I forgot to put your contact details down in here. So if you just want to let everybody know what your best contact details is if people want to get in touch.
Yeah, it's a really easy one. So hrv@fantech.com.au. And obviously Fantech is Fantech. and that'll come through to
So
myself.
HRV Guru, hashtag HRV Guru. I think someone said that
The
handle
other
was still
day.
available.
Yeah. And so that email comes through to myself or my colleague Nick. So.
Awesome. There is one on just a thanks from Jeremy. Now, Builders Declare also do a podcast. We're up to episode 13. It's called the Sustainable Builders Yak. And on the latest one, it's an absolute ripper. Simon and Brian catch up with Rob Campbell from eTool, where they're talking all things LCA, so life cycle analysis. They also touch on an amazing app that is out for $100. You can do a life cycle analysis in under an hour, which is an absolute game changer. And I'm super excited to use that myself. You can check that out on Spotify or wherever you get your podcasts or listen to your podcasts. This is likely to be our last webinar for the year. As you can imagine, December is just crazy for us builders on site. However, we have an absolute bunch of awesome webinars lined up for next year. Jesse Clark and Airboss Dan from Pro Climber are going to come on, and this is likely going to be a two-part webinar where Jesse's going to talk about the recent study he did with for Pro Climber, and then we're going to get the man himself, Airboss Dan, talking about more from a practical side of things installing the Pro Climber products. We've got Andre Grish from Big Windows talking all things high performance windows. We've actually got Rob Campbell from eTool coming on to actually talk us through what that LCA looks like, so that life cycle analysis looks like. We've also got the guys from Radial Timber jumping on to talk about their awesome products and also their really amazing sustainability credentials. I just want to thank you all on behalf of myself and also the other members of Builders Declare, and thank you for all the support this year. We actually have some huge news to announce early on in 2023, which may see Builders Declare looking a little bit different and with a heap more information to share, including a new website that's going to be launched. I know we've been threatening to do it all year, but we're pretty excited to be very, very close to having that launched. If you want to get in contact with us, it's info@buildersdeclare.com. You can join the conversation on our Facebook page and on Instagram. But for now, it's thank you, Joel, and for everyone coming along today. And, looking forward to seeing you all next year.
Lovely. Thanks, Hamish, and thanks all for your attendance. Nice to speak.
See ya. Bye.